Excuse me,
Yeah.
Günther, should I press Bildschirm freigeben? I see only a small picture of you at the moment. No, it's fine, okay.
Okay. Hello, Jakob.
Hello.
Hello. Oh. Hello, Nico. Good to see you again.
Hello, Rainer.
So, let's start perhaps. Thank you very much for coming back. I hope the lecture last time was not too childish, but I sometimes have a lack of seriousness. Yeah, before we come to a special pleasure today, I'll do the exercise from last time, and then we'll have the pleasure to hear Gerhard Betsch. This time he made it good into the song system, and he will talk about the early history of rings and near-rings. So yeah, from last time, we just have two small questions. One question was to find out what the type of a Boolean algebra could be. First of all, I ask you maybe to rename chapter 4. We had no polynomials so far. This will come today. So maybe we call chapter 4 what we had before, not polynomials, but maybe algebras and words, and we go to polynomials later on. So question 8 was about the possible type of a Boolean algebra. Well, in a Boolean algebra, you have the operations cap and cup. You have the negation, and since it's a bounded lattice, we have two elements, special elements, 0 and 1. And that's about it to make a Boolean algebra. So the type would be 2, 2 for cap and cup. Then the negation is a one-area operation, and these two are null-area operations. And so 2, 2, 1, 0, 0 would be an appropriate type for Boolean algebras. You could also do it just with cap and cup, but then the sub-algebras would not necessarily contain 0 and 1. They would not necessarily have or consider a complementation. And so the best thing to do this for Boolean algebras is to choose this type. The next thing is question 9. They are asked for, let's call a sub-variety of the variety of all abelian groups. And could any one of you find a nice sub-variety? So it's a V contained in the class of all abelian groups.
Yeah,
Any
one
idea?
could take two nilpotent groups, for example.
Two nilpotent groups. What would be the laws which defines that?
Yeah, x times x is 1.
Right. Yes. But two nilpotent groups, they are not interesting in the abelian case. Because in the abelian case, all of them would be two nilpotent.
Nilpotent.
Well, what would be a possible word or a possible law? We might take this to say that, for instance, 3 times x. Here, if we do it, if we write the groups additively, so 3x0, which means all groups which abelian groups which fulfill this have the law that 3 times every element is equal to 0. So these are groups which are of exponent 3. And so that's a possible way to choose V. We could take those groups of, say, exponent n. Then we might take it phi sub n, full groups of all, abelian groups of exponent n. They're characterized by the law that nx is the neutral element for all elements x. And this is a so-called Burnside variety, or a restricted Burnside variety. And one can prove that in the class of abelian groups, in the variety of abelian groups, there are no other subvarieties than these Burnside type varieties of abelian groups of class of exponent n. Yeah, then I would like to ask Gerhard Betsch to give us his account. But before you start, we all wish you happy birthday. You'll have birthday tomorrow, and like all the best for tomorrow and for the next year of your life.
Thank you.
Happy birthday.
Happy birthday, Betsch. Gerrit?
Do you all see me, and could you hear me? I have Grunewald in front of me, but not. Do you see me?
Yes,
I
we
do
can
see
see
you.
you and hear you perfectly.
Very good, very good.
Everything's
Let me let me start with this sheet of paper, historical background, which you possibly received, or is it?
So,
Okay.
Yeah.
Well,
here it is, yeah.
yeah. Okay. Well, yeah. Okay. I have to. Yeah.
Okay, so that should be.
Yeah.
That's good.
Yeah. That's the beginning. Around 1800 numbers. These were the normal numbers, integers, rational numbers, complex numbers. That was it. Gauss invented the Gaussian integers, but that was a special thing. And all people didn't talk on fields; they would talk on domains of rationality, and it was quite a discovery when Galois found out that there are finite domains of rationality, we would say finite fields. All fields which, the few fields which were known, were infinite. Now, Galois' works were not published at his lifetime. He died in 1832, and it took more time to make his works known. But anyway, in the 19th century, one knew there are finite fields, not only infinite fields. Then Hamilton investigated algebras, and he discovered, which we would think is absolutely simple and trivial, that the complex numbers are a two-dimensional algebra over the reals. And now he tried a three-dimensional algebra, which should be a division algebra. This didn't work. And today we know fairly well that he was looking for something which doesn't exist. And then in 1843, on October 16, on a certain bridge in Dublin, he had a very, very splendid idea, and that was the beginning of the investigation of quaternions, which are a form of four-dimensional algebra over the reals, and they were a skew field. That meant among the you could not prove from the axioms of a field except the commutativity of multiplication. You couldn't prove the commutativity of multiplication. There are real skew fields. This one was infinite, but there are skew fields, non-commutative fields. And Hamilton came up with a lot of wonderful applications of quaternions. This is not our subject today. Now, a big jump. In 1892, it was 400 years after the so-called discovery of America by Columbus. And there was Chicago wanted to make a great Columbian World Exhibition for reasons which are not interesting in our context. They couldn't do that in 1892, but they did it in 1893. But in this context, Chicago founded a university, and they appointed a very gifted mathematician, Eliakim Hastings Moore, right here, 1862 to 1932. As a professor of mathematics, later he became head of the department. And he was an energetic personality. He wanted not only a school of mathematics in Chicago, but a research center. He had himself a good postdoctoral study in Göttingen, and he invited he invited mathematicians from Germany and France and so on. And in fact, one of the prominent Göttingen mathematicians, Felix Klein, came to Chicago in 1893. There was a mathematical conference. There was an exhibition of mathematical models, German models, American models. Klein came and he made a 2 weeks lecture tour in the vicinity of Chicago. And this Eliakim Hastings Moore hired two people, Oskar Bolza and Heinrich Maschke, two friends. They both had a good education from Göttingen. And we must say he was quite successful. You see here Chicago mathematicians Could you please put it a bit more higher? In the period from the foundation in 1893 to 1910, they had 39 doctorates in Chicago, among the first of whom was Leonard Eugene Dixon, but also Oswald Veblen. He was an American with Norwegian background and others. At the same time in Germany, David Hilbert came up with his foundations of geometry, and in the Paris meeting 1900, he presented his 23 problems. Yet we should now possibly give, could you please show the sketch of the theorem of Desargues and of Pappos?
Okay.
Can you show that, please? This one. Yeah, okay. You see, in the old times, when Desargues was an engineer and officer in the 17th, 16th, 17th century, if you have two triangles and the corresponding points are combined by lines which intersect in one point Z, German Zentrum, then the corresponding lines intersect in points which lie on a line on the so-called axis. As long as geometry means normal geometry, Euclidean plane geometry, this is a theorem which may be proved. And also the theorem of Pappos may be proved. You have two lines, and on each of them 3 points, and you connect the proper points, then you get points of intersection which are on a so-called Pappos or Pascal line. Pappos, a generalization of the theorem of Pappos is due to Pascal. Therefore, people talk on the theorem of Pappos-Pascal. As long as you start with normal Euclidean geometry and its projective closure, these are theorems which might be proved. But at that time, people started to define a projective plane by geometric axioms. And it turned out then you cannot prove Desargues, you cannot prove Pappos. So it was clear, or it was at least a reasonable assumption, there are Desarguesian planes in which Desargues holds, and in the normal Euclidean plane it holds, or there might be planes in which Pappos doesn't hold. Now we should have the sheet of results.
So you want the
the sheet
yeah,
with
yeah.
results, please. Yeah, take it to you. It's not necessary to show it. So it Moore and his staff, they started now to investigate fields and to investigate projective planes from a more axiomatic point of view. I mentioned it was new that there are fields which are finite, Galois. And Moore asked the question, are there finite fields which are not obtained in the method by the method of Galois? Answer: no. Every finite field is a Galois field. Yeah. In this context, this has not. Should only mentioned in passing. In 1898, Maschke proved his main theorem on the reducibility of representations of finite groups. If you do representation theory of finite groups, Maschke is the main theorem. And now, 1905, that was a very productive year. One, there are very, very few skew fields known. The quaternions were known, and they are all infinite. Galois discovered finite fields. Are there finite skew fields? Answer: no. Every finite skew field is a field, which means that in the finite case, you can prove commutativity of multiplication from the rest of the axioms of a field. The proof by Wedderburn was visiting Chicago at that time. The proof of Wedderburn was erroneous. The first complete proof, valid proof, is due to Dickson, and a very elegant proof was given by Witt in his third semester. As a very young student, he came up with a wonderful proof, one-page proof. Every finite skew field is a field. There do not exist skew fields which are infinite, proper skew fields. And it was, if you look at what I called folklore, one had one knew that to a projective plane you may construct a coordinate domain, and on the other hand, if you start with a field, you can construct a projective plane over this field. It was relatively clear at that time, if you take not a field and not a skew field as coordinate domain, but something more general, you might come up with a plane which has nice properties, and that this was done in 1907. Veblen and Wedderburn, they constructed projective planes which were non-Desarguesian and non-Pascalian, or non-Pappian. Just by using as a coordinate domain the near fields which were constructed by Dickson. Now, would you please? We should come to we should come to the result of Dickson construction of near fields. Dickson, you may ask the question: is one distributive law may one distributive law proved from the rest of the axioms of a field? And answer: no. There are near fields, even finite ones, and Dickson constructed them using Galois fields. And so this opened up the, yeah, a whole bunch, an enormous variety of finite projective planes which are not non-Desarguesian. He did it with certain near fields, but it was pretty clear that this will also work with other near fields. Also, at this time, the question was, in a projective plane is defined by certain incidence axioms. In a projective plane, if it is Desarguesian, that was, well, then one could find as a coordinate domain a skew field, and if this skew field is a field, then even Pappus may be proved, and it was felt not completely clear that Pappus is equivalent with the commutativity of the coordinate domain. Now, very important, and a great achievement was Hessenberg's theorem in a projective plane. If you have the Pappus axiom, I didn't emphasize enough, Pappus and Desargues are now, if you work with axiomatic, if you work with projective planes defined in an axiomatic way, they are axioms. You cannot prove in any projective plane Pappus or Desargues. And Hessenberg showed if you have a projective plane which is Pappus, then it's automatically Desargues. And the converse is true in the finite case, because if you have a finite Desarguesian projective plane, then since it is Desarguesian, the coordinate domain must be a skew field, and it must be finite, and the finite skew field is a field. And since it is a field, you have Pappus. So in this case, the converse is true in the finite case. I should mention that this shows a very close connection and cooperation between Göttingen and Chicago. Dixon's paper, Construction of Near Fields, was published in a journal which contains news from the Göttingen Academy of Science. His second paper of 1905 on axiomatic considerations of groups and near field on fields, that was in Transactions of the American Society. So Dixon could offer this to the Göttingen paper. Yeah, now from our modern point of view, we could say, well, you have a projective plane. If you take a non-skew field, more general, then you can be sure it's not Desarguesian. And if it is non-Desarguesian, then it can be not Pappian. Veblen and Wedderburn had to prove a lot more, which today would be quite obvious. Today we have established the bijective correspondence between coordinate domain and projective plane. It's clear, yeah, full stop. It's, yeah, 2 weeks ago, the very close connection between strictly two transitive permutation groups and finite, strictly two transitive permutation groups and finite near fields were discussed. So it's clear, since the sharply two transitive permutation groups are very important, it was clear that it would be important to determine all finite near fields, because this gives a full overview on all strictly two transitive permutation, two transitive permutation groups. And Zassenhaus, who was honorar professor in German of Linz, Zassenhaus in 1936 determined all finite near fields. One would expect, since all finite fields were Galois. That was the result by Moore, which I mentioned. One could expect possibly all finite near fields would be those near fields which were constructed by Dixon were Dixon near fields. But unfortunately, the world is not so perfect. Zassenhaus determined all finite near fields, and he found all are Dixon, all finite near fields, all are Dixon, with 7 exceptions, which helped to have a full overview on finite sharply two transitive groups. I should have mentioned, or should have written on this sheet, later in 1981, Zassenhaus was able to show there are infinitely many infinite Dixon, infinitely many near fields which are not Dixon. So if we go to infinite near fields, things become pretty complicated. More so since we no longer have the strict connection between the sharply two transitive groups and near fields. We have a connection between sharply two transitive groups and near domains. But nobody knows a near domain which is not a near field, so far as I know. So there is a lot to be done. I would like to finish here, and now it's thank you for listening, and now it's Günter's turn to continue the lecture.
Well, thank you, Gerhard, very much for this interesting talk. You're really an expert on the historical aspects, and it was quite nice to hear that. Maybe I might mention that in this old days, the algebra was not, or looked different than it looks now. And I have at home an old version of the algebra book from Weber, which was quite in use in the late 19th century. And I looked at the definition of a field, and this definition extends over about 20 pages. So it starts with some axioms, and then 10 pages later, he mentions for a field we also would like to have this. You could never be sure when the definition is over. And so the style of algebra really has changed to the better, I think. And it's more, it's easier to understand things. On the other hand, algebra has become, I think, more complicated.
Yes, indeed. Yeah.
So thanks, and we'll come to chapter 5 now after the renaming, and chapter 5 will really be polynomials now. We have reached a point last time that we were able to define varieties, to define words and things like that. And if we look at the case of the variety of commutative rings with identity, I think I've denoted it that way, yes, before. So these are all the class of all commutative rings with identity. Words would look like that. They are everything which can be made out of X. And for that, we take perhaps X to be a singleton. So we take X to be consisting of X alone. It's complicated enough there. So words would be, for instance, things like that, X plus X, and again times X plus or minus 1, since we have an identity 1 here, and then again plus X squared, and so on. And you see that it really looks already to be close to polynomials. On the other hand, what we are missing in for real for polynomials are coefficients which are not only integers. You can get here all coefficients, also 2 or 3, as an operation of 1 plus 1 or 1 plus 1 plus 1, but you cannot get, say, the root of 2 as one of the coefficients there. So to get from words to polynomials, we need the coefficients, and the coefficients come from a special algebra, a special ring in here, while the words are independent of the ring you have chosen to look at. So these are words just in this variety over the commutative rings with identity. And in order to get coefficients there, we need the following setup. So now we start with an algebra A in the variety B, and we take an element A out of it, and we associate with every element A in the algebra a unary operation. Let's denote it maybe by this, square sub A, which goes from A to the 0th power into A, and A to the 0th power, I mentioned it last time, is just the set consisting of the empty set. So we only have to care what we do with the empty set, and the empty set should go to this specific element A. So we take here, we select the element A out of capital A, and this is a unary operation. And now we have in some way the constants there, which we like. So we take W, all words over all words in X over, and now we have to take the old system of operations, and we add all these unary operations where A is in A. And so we have now a lot more operations, just unary operations. And now you can speak about the element A, and you, in the words, you can now really get what you would like. You can get the usual polynomials again if we take V to be the variety of commutative rings with identity. Then the words now look similar to what we had before, but now we can take, for instance, as in algebra A, the real numbers. We forgot that it's a field because fields do not form a variety, as we have seen last time. And now we can form a certain words. For instance,
Don't we have the problem now that 1 times x is not x?
excuse me?
Don't we have the problem now that 1 times x is not equal to x?
Oh, yes, we have to add this as a law. Thank you very much. Yeah, I forgot that. So 1 times x is must be equal to x. It must be a unary in the sense. So, for instance, we have now 3.5 times x plus x squared, for instance, minus the root of 2 times x plus the root of 2 times x. This would be a word, and we see that this is a word in this in this variety over the real numbers. We have now the coefficients there, and we still have to find out what do we need to can we reduce it? Is this the same as 3.5 times x plus x squared? No, it's not, because the equality of words is really the formal equality. They must look like identical. And on the other hand, you would like to have these two things in some way identified. And now here also I agree with you, Jakob, that here we also have 1 times x is not the same as x. They look different. So in order to improve, or in order to come back to the class of rings where we are working with, we should identify these words which can be transformed using the laws which we have at hand in the case of rings. And so we might say that if we have two words, V and W, we might say that V and W are equivalent with respect to our variety V we're working in, if they give rise to the same functions, or if they give rise to the same expressions in every algebra in this variety, or which means that V and W is a law in this variety V. So two words are then equivalent if they form a law in this variety, And so we see that these two polynomials are, these two words are not the same here, but they are in this sense equivalent in RC1 to this, and this again is equivalent, if you like, in RC1 to 3.5 times x plus 3.5 times x squared. So you have the right to do all these manipulations, which are allowed in all rings which are commutative and have an identity. And now we are pretty close to what we would like to have as a polynomial, namely these are just the equivalence classes of words. And so we make a definition here. So we define a v of x to be the set of equivalence classes of these words which we had up here, factored by this equivalence class corresponding to the variety v. Well, that's finally the point when we have reached what we want, and we call this the elements we call them polynomials. So polynomials are equivalence classes of words, and it's looking like a lot of work to arrive at the concept of a polynomial. And we have seen in the beginning of the chapter 4 that when we had we had several restarts necessary in order to arrive what is really well defined. Good. So now we have these polynomials, and we can. I'll give some few facts which holds for all these polynomials in certain varieties or in all varieties, and then we look at a number of examples for special varieties, and we find that we get the usual polynomials back, but also we get the quite interesting and surprising cases in other varieties. So we might start with fact 1. With the same notations as before, we see that AV of x is, that's a set by definition, but we can make, we can use all the operations which we have in the variety v, and we can apply this to these words. This will give again words, and will give again equivalent words if they have been equivalent before. And so this can be made into an algebra again. And this algebra is again in this variety v. For commutative rings with identity, it means that the polynomials also form a commutative ring with identity and fulfills all the laws which are valid in all rings, commutative rings with identity. Now, this is pretty clear that this holds, because what since if VW is a law in V, then it means that V and W are equivalent words, equivalent with respect to our variety. And that means that the equivalence classes are the same. If we write this as equivalence class of V is the same as this of W. And so this law is also fulfilled in this polynomials. And we call this, of course, the polynomial algebra in X over V. So the fact 2. We can say that A is then a subalgebra, I denote it in this way, of a V of X. So these are what we later will call or have as constants again. And three, that A together with X generates AV of X. That's something what we would expect, and it really holds. It's not hard to see this and that. And now we can really say that the polynomials are generated by the constants and by the elements in X, because we have now AV of X, a framework where this generation can take place. Before we had this, we cannot say that A union X generates something if you're not in a big algebra where all this generation is possible. And so now things fall into place, and fact 3, fact 4, also the free algebra over X in V. This is a subalgebra again of AV of X. So you see that this contains the word free algebra. I haven't defined that. Free algebras, it's not really necessary. These are the algebras which have X as a basis, meaning that every map from X into another algebra in V can be uniquely extended to a homomorphism from Fx into V. So that's the diagram. X is contained in F. And every map from X to A can be uniquely extended to a homomorphism from F to A. That's the thing we know from linear algebra very well. Every vector space has a basis, and one of the characterizations of a basis is that every map which you define on the basis can be uniquely extended to a linear map. And that's the characterization of a basis which can be taken over to universal algebras, because the other thing with the linear independence and so on, that's not at hand here at the moment. If you take, for instance, the variety of commutative rings with identity, then the free algebra over one single x consists of everything you can make up of x, and that's the same as the words which we had before. And finally, that's another. Yeah, maybe I should add that for every variety, has a free algebra on sets of x as basis, where x can have an arbitrary large cardinality. That's something we know from vector spaces, that the size of the basis determines the vector space, because if two vector spaces have the have bases B1 and B2, and they have the same cardinality, then these two vector spaces are isomorphic. What about the converse? Can we have two free algebras which are free, which have bases of different cardinalities? And that can happen, but the theorem of Fujiwara tells us that if fx and fy have the same are isomorphic, then if x or if y are infinite, then they must have the same cardinality. And in the case of the finite situation, if both are finite, then we can say if the variety has an algebra of a finite algebra of which is not the which has more than one element, then this is also true. So this famous result in linear algebra, that the cardinality of the basis is uniquely determined, is true in many cases, but there are some exceptions where you can have free algebras over, say, different different dimensions, so to speak. And finally, fact number 5. That's again not, I don't define it completely, that a v of x is the free union of A and the free algebra over X. And that takes place in V. Now, what is a free union? It's again, one can define it by a certain diagram. And one also could introduce polynomials in this way, that you say, we show that in every variety free unions exist. And if you take the free union of A and Fx, the free algebra over X, then we have polynomials. But I think nobody has any idea from this definition, if we take this as the definition of polynomial, how polynomials really look like. Free union of A and Fx is, you can imagine this in such a way. You take A, the algebra A, you take the free algebra over X, take more or less the union, and you keep all the laws which hold in A. On one hand, you keep all the laws which hold in F sub X, but you don't add any connections, any laws between A and f sub x. So you have two different algebras here. You take the union, but you separate them. They have no relations between them. So it's some sort of an apartheid product, because in this case you really separate them completely, and that's in another version nothing else than the polynomial algebra. But again, I've never seen somebody who sees this definition of a polynomial and says, now I know what a polynomial is. So now it's time to look at some examples and find out how polynomials look like in special cases of varieties. Of course, the first example would be, again, the commutative rings with identity. What would be AV of x? And let's take, again, x to be the set consisting of x alone. It's sufficient to find out. Yeah, we have seen before that they look exactly like polynomials which were used at. So it's of the form a sub naught plus a sub 1 times x plus up to a sub n times x to the n, where n is in n sub naught, and where the a sub I are in a. Now, why is that? We have seen before that we have some parentheses, root of 2 times x plus x squared or so, but we can always reduce the polynomial to such a form, because whenever you have parentheses, you multiply them out. You have commutativity of addition, you have commutativity of multiplication, to order things in such a way that we get just the usual polynomials which we are used from early childhood. Okay, that's even more than we might expect, because polynomials are equivalence classes of words, and so one should better write the equivalence class of this. But what we take here is a system of representatives. It's always much nicer to work with systems of representatives instead of equivalence classes. And here you have the complete list of representatives of the equivalent words in the variety of commutative rings with identity. In fact, you have even more than that. You have more or less something like an algorithm which tells you if you start with some word 3 times the root of 2 times x plus x to the third or so, you know how to arrive in this version. Whenever there's a parenthesis, multiply it out and order it appropriately to get into this form. And so this is not only a system of representatives, so it's even more. It's what is called a normal form. So we have something which is much better. We have a normal form. A normal form is a system of representatives together with an algorithm which tells you how to arrive to your representative. We'll find later on some examples where we will not get a normal form and where the determination of the elements is more complicated. Okay, now take R1. Maybe not commutative rings with identity. And how does a B of X look like here? Well, it's certainly you have any A sub naught here. And then you have, say, A sub 1 times X, as before. But now we cannot use commutativity because that's not a law in the variety of all rings with identity. And so we have to add some maybe X times A2. And yeah, since, yeah, okay. And then we can add some A sub 3 X times A sub 4. And then we might take A sub 5 times X squared, and so on. And you see, it's much more unpleasant because you have all kinds of polynomials now, and it's not possible to bring it into this form as before. But on the other hand, you see that you can find also some sort of a normal form, because if you multiply parentheses out and then you have to order it, but now the normal form looks more difficult. You have to have one constant A sub naught, then for products of two elements, you have two candidates. You have to take care of those, and the X can stand in the middle. So if you work out a normal form, you will arrive at the normal form finally, but it's not so pleasant, of course. On the other hand, we all know from linear algebra that we need polynomials of this type, because, for instance, if you take matrices, and if you would like to find, say, the characteristic polynomial of the matrix, then you have polynomials of the form A plus B times X plus C times X squared, and so on, where A, B, C, and so on are matrices. So that arrives, appears in the context of forming the characteristic polynomial, which you need for the eigenvalues and so on. And so you get really polynomials which you cannot form, like in the case of the commutative rings with identity. You're out of that. And now this also gives the explanation or the solution to the thing I mentioned at least 1 week earlier. Is X times 3 the same as 3 times X? And who decides if this is the same or not? And I ask, can the Pope decide it, or the President, or whatever? Now, the one who decides if this holds or not, the one that's you. You decide if you work in the variety of commutative rings with identity or not. So if you start with algebra A, which is a commutative ring with identity, like the real numbers, you can view the real numbers as an element of RC1, and then 3 times X is the same as X times 3. You can view the real numbers as in the variety, as a member of the variety of all rings with identity, and then they are not the same. So it depends on the variety you choose to work this, and you see it was a good idea to write the variety as a subscript here for the polynomial algebra. So the polynomial algebra, of course, depends on A and on X, on the selection of X, and it depends on the variety you are working in. And so that gives the answer to the case when somebody writes, we would like to have polynomials in commuting variables or not. He or she means that they are working in this or that variety, and it's a good idea to say before you start considering these polynomials to tell in which variety you are working at. Now, what about all rings? What would polynomials look like? Now, AV of X would consist, of course, of all of those as well. But now you have another thing to consider. You have no unit element anymore, or not necessarily. You cannot use it. So you have to other polynomials. For instance, X. X will not appear here because you have you do not have a 1. And so the same as x squared or x to the third times a and things like that. Since you don't have an identity, you cannot subsume this under this condition here. And now you see it's pretty tough to find a system of representatives. I simply made life easier in writing down a few examples what you might expect, but to give a concise form of all what you have to appear here is possible, but it's a bit unpleasant because you have the lack of an identity really makes life difficult here. Now, what about some completely different things? So now to something completely different. Take the variety of all groups. What would AV of X be? Again, you can think these are words in A and X, and you can use for simplification all laws which hold in V in the variety of all groups. Yeah, what can you expect here? You can expect here again A sub naught. The constants must be there. Then let's take again the set X to be a singleton. Then you can have X, but also you can have say X plus X here, or minus X minus X minus X. So it's a good idea to say we take C1 times X. Well, this is an integer, and it means minus 3 times X means minus X minus X minus X as an operation. But then there can be another A sub 1, and then there can be a C2 times X, and it can go on. You see, I write it additively to have a more to have better memories to the polynomials we're used to, and that goes up to, say, to some z times n x plus a times a sub n, so that the a sub i's are in a, and the z sub i's are integers. And so you see, that's how polynomials over groups look like. We can bring it into the form y, if you have any mixture of constants and x's and constants and x's, we always might, if we have 2 or 3 x's in a row, we might turn them to, in this way, to set 1 times x. Then we wait perhaps another constant and so on. So it's pretty easy to find that this is a system of representatives of polynomials over groups, over the group A, and it's even a system, it's even a normal form of polynomials again, because what I said now is the algorithm. Whenever you have, say, x plus x minus x minus x plus x, then you abbreviate this by simply, in this case, simply by x. Because in every group you can do this, and so you can do it with the x's, and so you can really arrive at this normal form. Much nicer is life, however, if you have the abelian groups. How do the polynomials look like now? Well, now we have a commutativity of addition, and so we can do things much easier, because we can collect all the constants before. So it's a set of all, say, a plus z times x, where a is in a, and z is in the integers. So now that's simply, that's very nice here. So polynomials over abelian groups have a very nice form, and the same happens if you take marshals over ring R. Then the situation is simply the same. You have all A plus, and then the ring elements times x, and so you get also a nice normal form for polynomials over abelian groups, or polynomials over marshals over rings. And if you have polynomials over marshals, then you also have polynomials over vector spaces. They also look this way. Of course, the more laws you have, like commutativity, the smaller the variety will get. And that's clear. If you add more and more laws, it's getting harder for algebras to fulfill all these laws. And that's something which you know from daily life. The more relatives or friends you have, the harder it is to be in good relations to all of those. So you get smaller and smaller varieties, but on the other hand, you get much nicer forms of polynomials, and so we have the next questions for next time. It's now question 10. What are the polynomials AV of x? How do they look like if V is the variety R1 of all rings with identity? No, of the commutative rings. With the rings with identity before. And question 11, similar for the case that V is the variety of Boolean algebras. So how do the polynomials over Boolean algebras look like? And for that, we need to get a variety. We need to have the Boolean algebras of this type 2, 2, 1, 0, 0, as mentioned at the beginning of this today's talk. Now, this is in some way exotic because in all the cases you had before, rings and groups, you had already something like a group to start with, and then maybe you have additionally some multiplication, or as in the case of R modules, you have the multiplication by elements of R and so on. But you had already in all these cases at least an additive group. And so we call this a so-called omega group, or a group with multiple operators, or how it's, as it's called now mostly, it's called an expanded group. That's an algebra of type. First we have, let's write it additively again, plus, minus, and 0, union with some other set of operations. And here you see that you have such that this algebra A with plus, subtraction, and 0 is a group. So you have a group and maybe some other operations, but at least you have something. That means you can speak of normal subgroups and all these things. So examples, of course, groups, rings, vector spaces, R modules, and so on. And if you have an expanded group, life becomes much easier. And it becomes much nicer, of course, because we can do the following. So let A be an expanded group. Let X again be the singleton X. Then you can form expanded group in the variety V. Then you can do the following in the corresponding polynomial algebra. You can define the substitution of polynomials. Well, you can do it also for other, not necessarily expanded groups, but the substitution, the composition is now much more interesting. What you can do here is now you can define the composition. And again, we use the circle of polynomials in this way that if you have two polynomials and then you replace in the first polynomial the x whenever x appears by the second polynomial as usual. And so we have now addition at hand because it's an expanded group, and composition, and it's easy exercises. exercise then to see that then AV of X together with this addition which we have and with composition is of course a nearing. So finally we get back to nearings after a long deviation to universal algebras. But now we know exactly what a polynomial is. We know what the X is. It starts from the chosen set capital X. And we see that in the case of expanded groups, we get nearings in particular in the case of groups itself. So the polynomials over a group, they form a nice nearing, and we'll look at this nearing then again in more detail. Of course, if we have a ring, then a commutative ring with identity, we get the usual polynomial nearing out of this. And it's perhaps a good time to stop now. And next time we'll start to look at polynomial nearings over certain varieties in more detail, what we can say about these and so on. What you have not met so far is the thing which is connected with, say, polynomial maps. Polynomial maps will also appear soon, but they have well, they have a lot of things to do with polynomials, but they are of a completely different nature. And so it's a very good idea to keep these polynomials and polynomial maps apart, except in some special cases, which we will also discuss next time. So thank you very much again, and thanks Gerhard again for your contribution, and hope to see you next week again. Have a good time, have a good week, and try to stay healthy in these difficult times. So all the best, and see you next time then.
Thank you.
Thank you.
Bye-bye.
For the
Bye.
lecture,
Thank you.
goodbye.
Thank you.
Thank you.
Goodbye.
Goodbye. Thank you.